Section 5.5, bases other than E and applications. Let's recall something from your Algebra 2 days regarding logarithms. Since your calculator can only evaluate logarithms for the base of 10, where we use log x, or the base of e, where we use natural log of x, a formula is needed for changing the base when you are working with other bases. And that formula is log base a of x. In other words, a to what power gives x can be found by log x over log a, or ln x over ln a. Or you could rewrite this as 1 over ln a times ln x. Notice that ln a is just some constant. Remember, we have learned that ln of a over b is ln a minus ln b. It is not ln a over ln b, which, as you can see, is your change of base formula. So what is a way that we use this? Let's say I have log base 5 of 10. Remember, a logarithm is an exponent. That means 5 to what power is going to give me 10. And since I can only operate my calculator in base 10 or base E, then what I can do is write this as log 10 over log 5, or ln 10 over ln 5, natural log of 10 over natural log of 5. And we do that calculation, we get approximately 1.43067, and it continues. Let's remember, for AP answers, we want to round to 3 places past the decimal. That would either mean truncating, chopping it off after the 3rd decimal. You would write 1.430 because it's not exactly 1.43, so you can't write 1.43, 1.430, or you could write more decimal places. You could also round that. Since this is 6, we could round this up to 1.431, or you can actually just write several decimal places. They stop reading it after the 3rd one. It must be correct to 3 places past the decimal. And what this means with our number is that 5 to that power is going to give me 10. Okay? And here's a nice little explanation of why this formula works. If I take y equals log base b of x and I write it in exponential form, I get b to the y is x. Since we are going to solve for y, and y is our exponent, we need to take the log of both sides, which allows us to bring down that exponent. And solving for y, we're going to divide both sides by ln b. So how do we find the derivative when our base is something other than e? Well, the derivative with respect to x of log base a of x is the derivative with respect to x of natural log of x over natural log of a. Let's remember, natural log of a is just a constant, so I can rewrite this like that and bring that constant out in front. Now we want to find the derivative of natural log of x, which we know to be 1 over x, and we still have that constant 1 over ln a in front. And we can clean this up. You often see it like this, 1 over x times ln a. Can we write it like that? Sure. But we usually bring the coefficient, in this case, the variable as the coefficient, so we don't accidentally write ln ax. So resulting from this, we have this log base a of x is 1 over x times natural log of a. Similarly, log base a of u is 1 over ln a times u prime over u. The derivative of ln u is u prime over u. Okay. And again, this can be written like this. You can write it however you want to write it, in which way you understand it best. I like this way the best because it keeps it clean, but whatever. So let's recall, we know that e to the natural log of x is x, and e to the natural log of u is u. Therefore, if I have e to the natural log of some constant a, we know that's going to be a based on that property, and e to the log base e of a, notice bases are the same, is equal to a. Just some little manipulations. So this makes us wonder, what happens, what am I thinking about when I have some base other than e raised to a power? A to the x could be thought of as e to the ln a. Remember, e to the ln u is u, so e to the ln a is a raised to the x power. We know when we raise a power to a power, we multiply the powers. We know x times ln means natural log of a to the x. So e to the natural log of a to the x is a to the x, because e to the ln is a. So recall that the derivative with respect to x of e to the u is e to the u times u prime, or du dx. And the fact that we know ln is actually a constant. So the derivative with respect to a of a to the x is, remember, a to the x can be written like this. So e to the x ln. We know that the derivative of e to the u power is e to the u times the derivative with respect to x of our u. We know that this is a constant. So that's ln times the derivative with respect to x of x, which we know to be 1. And this gives us that the derivative of an exponential function is the exponential function times the natural log of the base. The derivative of an exponential function is the exponential function times the natural log of the base. So this lets us know that the derivative of a to the x is a to the x times the natural log of the base. Similarly, the derivative of a to the u is a to the u times the natural log of the base times u prime du dx. So remember last section where I said, well, I'm not teaching something completely correctly. Let's look at the derivative with respect to e to the x. According to this theorem, it says the derivative of an exponential function is the exponential function times the natural log of the base. So that means that really the derivative of e to the x is e to the x times the natural log of the base. Well, we know that the natural log of the base is 1. ln e is 1. So that is how we got the derivative of e to the x is e to the x. But really, we just skipped this part because we took for granted that we know ln e is 1. Okay, so let us remember, the derivative of an exponential function is proportional to itself. What does that mean? It is the exponential function times some constant, which happens to be the natural log of the base. So let's just think ahead. What if I wanted to undo that derivative? Notice a to the x dx. Well, notice the derivative of a to the x is a to the x times ln a. So what is missing here? My factor of ln a is missing in the integrand. Okay, so I need to multiply and divide by ln a. That is now the complete derivative of a to the x. And so what is the integral or the antiderivative of a to the x dx? Well, I have to fix the integrand. And we can see that clearly that answer is going to be 1 over ln a. And I got this exactly in that form, times a to the x plus c. So as for the integration of a to the x, since a to the x is the derivative function in our integral, remember we needed ln a, so I'm going to multiply and divide by the ln a in order to get what we need. So if u is a to the x, du is a to the x, natural log of dx, and so from our last problem, integral of a to the x dx, we need to multiply by ln a and divide by ln a so that we have a to the u du. And so that is the anti-differentiation. Don't forget your plus c. And that is what this is showing. We needed to multiply and divide by ln a. Now I have my du, and the integral of du is u, and my u is a dx. So again, here is our theorem. The integral of a to the x dx, remember, we are missing that factor of ln a. So we have to multiply and divide by that factor of ln a, which is how we get this, which you will often see written like this. Now here it says to see examples 1 through 5 in the textbook for applications of differentiating and integrating deals with half-life and what we know about half-life. So half-life, a sample contains 1 gram of carbon-14. How much will be present in 10,000 years? So the half-life, okay, and we write this as y equals 1/2 T divided by 5,715 because the half-life is 5,715. So T over that. So Y is, when I have T to be 5,715, that 1 gram becomes half a gram. That's what that means. So when T is 11,430, the amount is reduced to 1/4 of the amount. Okay, 11,430, which is twice that. So we know that we want our sample after 10,000 years. Okay, our time is 10,000. And that's going to be how much is left after 10,000 years. After 5,000 years, it's a half. So we need it to be less than half, which it is. You've done this in science. Example 2, make sure you know how to do these. Solution is below. I would think about doing this one this way. 3 to the x equals 1 over 3 to the 4th. So 3 to the x equals 3 to the negative 4. Bases are equal, exponents are equal. What about this one? I would think about doing this as log is exponent. There's my exponent on 2. 2 to the negative 4th equals x. There's your answer. But I could also, what this problem is doing is taking 2, it's raising this power as an exponent on 2 and this side as an exponent on 2. And 2 to the log base 2 of x is x. And of course, 2 to the negative 4th is 1 over 2 to the 4th. Example 3, finding derivatives of each function. Example 4, integrating with a base other than e. Example 5, comparing variables and constants. Be sure you look at that. Really be sure of this, x to the e. Remember, e is just a number. It is not a variable. So we can use our logarithm power rule. But here, we cannot use our logarithm power rule. X is not a number. So we need to take the log of both sides. That allows us to bring down that exponent here. Now we're going to solve for y prime. So the derivative of this side using chain rule, y prime over y, the derivative of ln u is u prime over u, in this case y prime over y. Here we got to use the product rule. X times the derivative of natural log of x plus natural log of x times the derivative of x. So this is a good problem to look at. This is a good problem to look at. Here is something you should have seen in pre-cal. E is the limit as x goes to infinity of 1 plus 1 over x all raised to the x power. And again, another way to write that expression on the inside is x plus 1 over x. And we actually did this when we were looking at the limit as x got really big way back in section 1.2. But if you take this, okay, and you let x be 10, 100, and so forth, and increase, you can see you're getting closer and closer to that value that we know to be e. Now, that takes something here. We recognize this, you should recognize this from Algebra 2 and Pre-Cal as your compound interest formula. Okay, the amount you have is the principal times 1 plus the rate over the number of times compounded per year raised to the n. Well, if I take the limit as n goes to infinity, we know this piece becomes e. And also, as we go to infinity, we want to look at n and r over n and write it as 1 over n over r. We're going to take n and write it as n over r to the r. If I take n, the nth exponent, I can write it as n over r to the r, because when you raise n over r to the r's cancel, you're left with n. And the cool thing here is we get this to be x, we get this to be x, and there's your formula. So here is our compound interest formula, where the amount we have is our principal, what we've invested, what we started out with, times 1 plus the rate of investment over the number of times that is compounded per year, raised to the n times t. That is another way to do this. Remember, raising it to the n times t is the same thing as raising this to the n and then raising that to the t. And then if we let the limit as n goes to infinity in this, we would get a equals p e to the rt. Principal times e to the rate times time. And then you're asked to look at example 6. A deposit of $2,500 made in an account that pays an annual interest rate of 5%. Find the balance in the account at the end of 5 years, so that's your time. If the interest is compounded quarterly, so the number of times per year here would be 4. The number of times per year here would be 12. And continuously means every second of every day. So that's a different formula. So A equals P times 1 plus 5% interest rate is 0.05 divided by quarterly, 4 raised to the 4 times T for 5 years. We get that. Now let's do that and compound that interest in 12 times a year. So my 4s become 12 and I have a little bit more money. Now let's compound it continuously. That means that this formula changed to this formula and we get that. So we definitely want to go with continuous compound interest when it's paying us money. We don't want to have that when we're paying off a loan. And finally, bacteria culture growth. Okay, a bacterial culture is given by this logistic growth function, which we're going to look at more in chapter 6. So y is 1.25 over 1 plus 0.25 e to the negative 0.4 t, where t is greater than or equal to 0. Where y is our weight of the culture in grams and t is the time in hours. Find the weight after 0 hours, 1 hour, 10 hours. What is the limit as t approaches infinity? So this is simply calculator manipulation. Substitute those numbers in, and you can see what's happening as time increases. Of course, the weight of the bacterial culture is increasing. And what happens if I take the limit as t goes to infinity of this? Let us remember, let us think about what this is. The limit as t goes to infinity of 1.25 on top. 1 plus, what does this negative exponent mean? It means 0.25 on top of it, and on bottom, it means e to the 0.4t. That's what that negative exponent means. Now, as t goes to infinity, I get 1.25 on top, I get 1, but this, as t goes to infinity, that becomes 0. It's just another quick way to figure out how long it's going to take your money to double. And they use different formulas. I think now it's 74. And then we just looked at this exponential model for growth. Okay, your TPs are number 17, 21, 39, 43, and some even ones, 62, 68, and 90. See you next time.